Welcome to the second week of lectures for CMPT 300, Operating Systems at Surrey. In this week's segment, we will be dealing with processes and threads, the vessels of execution in an operating system. That is, if you want to run any application, it runs as a process. And we'll see what threads are in a few slides and look at the differences between them. All right, but first, a little bit of understanding on how processors work in general and what actually runs on the hardware, as opposed to what is the abstraction that's exposed by the operating system to the applications, right? So a little bit of computer architecture 101. In general, processors have registers. These registers are your primary state in your program. Pay particular attention to this one called the PC. Okay, the PC at any given point indicates what part of the program is running. Okay, so if you have a program with lots of instructions, then the PC indicates which instruction is actually running on the CPU. And as you're going through the system, essentially the PC increments one at a time. So it does the first instruction, then it does the next one, so on and so forth. And each of these instructions operate on pieces of data that could either be in memory or they could be in registers. Okay, so they input the data from registers or memory, and they output the data back into registers or memory. Okay, so essentially instruction execution is a big giant loop. So it's a loop that goes around and keeps repeating itself again and again, where every single time the instruction under the given PC is run before it moves on to the next one, and so on and so forth. A thread of execution is an independent loop of fetch, reading the instruction, decode, which looks at what the instruction is, and execute, which essentially runs the instruction. Okay, uniprogram refers to one thread at a time. So early Macintosh computers, DOS systems, almost no known systems today are uniprogram. Okay, just for the sake of utilization. If you have only one program that's able to run at a time, then your machine doesn't see as much utilization. In fact, what's the point of having multiple processors, right? But just simplify a lot of things for the operating system builder. Over the next few weeks, we'll actually look at why single-threaded programs are just so much easier to reason about. Okay, and essentially they get rid of this notion called concurrency by defining it away. So if you have only one thing running at a time, you don't have to deal with side effects. For example, what if two threads or two processes try to manipulate the same data at the same time? Such things cannot happen, right? Because by definition, you have only one thread which touches one piece of data at a time. Multi-programming essentially refers to more than one thread, and almost all known systems these days are multi-program, including the ones on your phone. So you've got Unix, Linux, which are classical multi-program systems. The first one was actually Multics, the first popular one. Obviously, there did exist a few multi-program ones before them, but they didn't reach the level of popularity that Multics did back then. And you've got Windows and Mac OS, and of course things like Android systems. We'll get to the specifics of how multi-programming systems like Android or iPhone differ slightly from systems like Linux. Okay, Android is more similar to Linux. In fact, it is Linux underneath, but the early versions of iPhone had some subtle differences, and we'll look at what those differences are. Concurrency versus parallelism. These are two keywords that you will hear often as interchangeably, and these terms are often used in systems. When I use them, I just want to disambiguate between the two. So concurrency, as I define it, is essentially from the application's perspective. That is, the application consists of multiple threads of execution. So concurrency is an application having 1,000 threads. Or, for example, if you have a web server, then you have a front end which parses the request, a back end which actually fetches the data and sends it out. Parallelism, though, is from the hardware perspective. So concurrency, while it's unbounded typically, so you can have as many threads as you want, and the number of threads per application varies based on the application. Parallelism, on the other hand, is fixed. It's fixed for a given system. It's just based on how many processors you have. So a concurrent application can be executed on a single or a multi-CPU hardware platform. So it can be executed on a parallel platform or a non-parallel single platform. Okay. The basic problem of concurrency is, if you think about it, to keep things simple, and multi-core systems are just an extension of the single CPU platform, we will talk about single CPU platforms. So from here onwards, throughout this week's segment, all systems we talk about you can think of has only one CPU. Okay, a multiple CPU system just takes these components and replicates them for each CPU. Right. So essentially, what we're going to do is talk about a concurrent application running on. Give me 1 second. Okay, we're going to talk about a concurrent application running on a single CPU platform. So parallel application, lots of threads, but there's only one CPU. So the question is, if you have lots of threads, obviously you got to run each of them on the CPU, right? So you got to give each of them some time on the CPU. So, except that the application doesn't want to have to deal with this for the following reason. So if the application had to forcefully manage not just the fact that there are these threads, but also when and how they get time on the CPU, then that's going to be a lot of burden on the application. Furthermore, each application would have to do this on its own. So while you're vending the process of giving each thread time is similar across a lot of different applications, each application would have to write its own library just for scheduling itself on the CPU. Furthermore, what happens if you want to have different policies? You would have to go back and change the application code. Right? So essentially, the basic problem we deal with is to provide the illusion to each thread that it has exclusive access to the CPU. So the applications themselves are not aware of whether they're running on multiple CPUs or a single CPU system, or even how long they have on the CPU itself. So it's up to the operating system to vend out time. So you've got a single resource. Lots of different threads want access to the single resource. Our goal in general is to provide exclusive, transparent access to the single resource. In this case, it's the CPU. So what we're dealing with is your application has specified your vessels of execution, which are your threads. The hardware resource you have is one CPU, and you're mapping these threads onto the CPU over time because there's only one of them. And at each given instant, there's only one thread running on the CPU. And each thread itself is completely unaware of the existence of these other threads. And the OS, the primary job of the OS is to coordinate these multiple threads. So multithreading. So we'll deal with the specifics of what multithreading is. So the key challenge with multithreading is how to provide the illusion of multiple CPUs with a single CPU. So the goal is the illusion of multiple CPUs with a single CPU, all right? And the solution essentially is to multiplex in time. So here time goes left to right. And if you look at it, each thread gets a certain amount of time over the whole time. Okay, so each thread, you take all your threads, and you pick the first thread, you give it a little bit of time. Then after a while, you take it out, give the next thread a little bit of time, take it out, give the third thread a little bit, and so on and so forth. And each thread itself has a data structure, which is called a TCB. In Linux, it's called a PCB, a process control block, or a task control block, which has this notion of a program counter, stack pointer. We'll get to what the stack is in a second. Register values. This is all the state that you need. This is hard state. So all the state that you need to checkpoint in order to be able to restart the thread. So for example, if you stop the thread 1 at this point, and then you want to bring it back in after thread 5 over here, so let's say I want to run T1 here. Okay, if I want to run T1 here, then I need to be able to restart it, right, from where I left off. Where I left off, how do I know where I left off? So the PC, stack pointer, and the register values essentially specify where you left off the thread. So you continue from where you stopped. You don't want to redo all the work. Okay, we'll get to what the stack is and all of that in a second. Okay, so how do you switch from one thread to the next? You save the PC, the stack pointer, and registers in the task control block, and you load the PC stack pointer register from the new task control block from where you want to continue. And what triggers a switch? There are a lot of different possibilities for this. There are timers, so after a fixed amount of time, voluntary yield, where a thread, after doing its own work, gives up, saying that it's done with its CPU and someone else can use it. Or I/O, which is essentially long latency operation. If a thread hits a point where it's going to take a long time to do something else, like for example write to the disk, then it wants to give away the CPU to someone else to use, right? It's going to take a long time doing something else, so the CPU is going to be idle during this whole point. And so that is another possibility as well.